This is, as others have eloquently mentioned before, I'm here to take credit for the work of many others, and this is, my core team, which you might notice is heavily weighted in terms of the gender distribution toward women. So, and I understand, there are folks in this group who appreciate, the promotion of women in data science. So I'm very proud to work with such a competent team of collaborators. We also have a number of advisors working in related areas. I'm going to kind of go kind of quickly because I have like an hour's worth of stuff to tell you in about 18 minutes. So I hope you had coffee. So again, there's this idea that there's a complementarity between what machines and humans can do. And so, we kind of anticipate that over time, as AI methods improve, that they will progressively be able to do more and more of what humans can do today. And we're seeing that happen. And I think, Eric's doing some of the most substantive work that I've seen in the area, for example, in terms of acquiring real-world knowledge about physics just through machine-based learning. One thing, though, just as sort of a thought experiment to you, the most interesting things to me about Eric's talk were not what the machines could do, but what the humans did. So he showed a slide of the patient record, and he said, this particular observation having to do with the intestines and the presence of the drugs that tend to slow that stuff down, led us to do this other investigational study. Well, it took a human to actually notice this thing, recognize that there was an anomaly there, and more importantly, realize that that was an important anomaly. There were probably lots of anomalous, spurious kinds of things, but one of them mattered. And why is it that the human had to be in the loop to figure that out? Why couldn't a machine figure that out? What's missing in terms of what machines can do? And the other example that I thought was worth mentioning is, with that wind mapping thing. So we have these gems, hidden gems, but it takes a human to realize that they're hidden gems and figure out what to do with them. Why human and not machine? So that's food for thought. So anyway, we believe that, in the future, maybe AI can do some amazing things and solve problems for us that we can't solve today. But today, right now, we can take the best of what we've got in AI, and we can take humans, which today exhibit the most human-like intelligence, and have them actually work together. And we wanted to take this approach and apply it to a real-world problem. And serendipitously, at the time that we were looking for a problem, I was introduced to a biomedical researcher at Cornell University named Chris Schaefer, who was studying a particular aspect of Alzheimer's disease and had made some important discoveries related to brain blood flow. So we've known since the beginning of Alzheimer's disease that there's about 30% less brain blood flow in Alzheimer's patients than in healthy brains, but we've never understood why. And so the important discovery is that it's these tiny blood vessels in the brain called capillaries that were found to be stalled at a higher prevalence rate in Alzheimer's, in mouse models of Alzheimer's disease than in the wild-type mice. And then it was sort of like 2% in the Alzheimer's mice versus 0.5% of capillary stalls in the wild-type mice, which doesn't sound like a big difference. But then when they looked at the downstream effects, the overall reduction in brain blood flow was actually about 30% due to those stalls. And the other important discovery they made, quite serendipitously and accidentally, was that introducing an immunosuppressant, it was actually, they were just using it as a way to sort of to tag some things they were looking at microscopically, but it had this unintended effect of releasing the stalls. So that suggested that there was an immunologic response causing the stalls, which ultimately was connected to the hallmark characteristic of Alzheimer's disease, which is the amyloid oligomers. In further studies, they found that restoring the blood flow to the brain in these mice actually restored the mouse memories, reduced other cognitive symptoms, depression, And so it looked like a promising avenue for additional research. So, so there are a number of research questions that need to be asked that all involve counting these stalls in the mouse brains. The problem they had is that in conducting a single experiment, they would generate so much data that it would take 6 months to a year to answer a single research question, which is, of course, a glacial pace when it comes to research. So this wasn't very practical. And I'll sort of cut to the chase. We figured out that we could sort of crowdsource this data analysis task. So we created an online game that anyone can play called Stall Catchers. And by playing the game, you're not a subject in the experiment. You're actually analyzing the data along with or on behalf of the scientists. So we have about 12,000 people registered in Stall Catchers. This is what it looks like to play the game. So we show you a virtual microscope. We stole this interface from the Stardust at Home project, and we adapted it with their help. And the idea is that you look inside the outline, add an individual capillary, and you just have to make a single binary force choice decision about whether the blood vessel is flowing or stalled. And that's how you play the game. So we have, like I said, 12,000 registered users day to day. You might see 50 to 100 people playing the game. We have the usual sort of distribution of kind of like, sporadic users, periodic users, and super users. Today, we're analyzing the data about 3 times faster than in the lab. So now we can answer research questions in 2 to 3 months instead of 6 months to a year. And for this reason, the researchers are actually asking questions they otherwise wouldn't have been able to ask because of the high cost of analyzing the data. So they're actually doing more research and asking more in-depth questions than they otherwise would have been able to. Stall Catchers is the first and only collective intelligence system for Alzheimer's research data. And we have some research results. Recently, the community finished analyzing a data set. It was about 105,000 capillaries from something like 30 animals. And the question was whether or not, regardless of whether the mouse has Alzheimer's disease or not, whether having a high-fat diet would increase the incidence of stalls. And so the preliminary result, this hasn't been vetted by the Cornell lab yet, but is, and it's very statistically strong because of the amount of data, is that it was, quite higher stall rate with a high-fat diet. The current data set in Stall Catchers is asking more about the upstream molecular mechanisms that might be implicated in this stalling process, because if we can interrupt that safely, then we could, potentially pursue a treatment that does the same thing in humans and restore blood flow to the brain, which hopefully would alleviate the cognitive symptoms. Stall Catchers has also had this ancillary effect, which the Wired journalist thinks maybe is one of the most powerful effects, is that it's a very hopeless and helpless feeling disease, and so it gives a reprieve to caregivers and even patients who play the game, and they can feel like they're making an impact in the research that could help them within their own lifetime. So this is, sort of the substance of what I wanted to talk about here, because this involves, the generous compute time from our Azure grant, and we've made, I think, pretty good use of that time. So there are different sort of human-machine partnerships that we've had in this project. Originally, so I'll just go over the 3 basic components. So first of all, we have to figure out where are all the blood vessel segments in the images, and then draw an outline around them, because that's the only way we can show a human, this is the one you're supposed to look at, this is the one you're supposed to annotate. We get really noisy data sets. Sometimes we get arterioles or venules that are huge, and we draw these weird outlines that really don't mean anything. And then it's wasting people's time because they get served one of these videos and they're trying to annotate it. They don't know what it is or what to do with it. We have a mechanism that allows them to flag bad movies, but it's still wasting their time. So we are exploring machine-based approaches to doing that. And then ultimately, we have to do a classification. We have to count how many vessels are flowing and how many are stalled in order to answer the research questions. So at the beginning of the project, we actually thought we were going to have to create 2 different crowdsourcing platforms. One to find the vessel segments and one to do the classification. And for finding those vessel segments, we had to come up with some way to automatically trace the vasculature in these 3D image stacks. And so we were going to beg, borrow, and steal from the EyeWire platform, which is used to trace the retinal neurons, and try to adapt that to the vasculature. And ultimately, though, we sent one of our team members to Princeton to study for a week with Sebastian Sung, who created EyeWire, and learn about their convolutional neural network methods and how they were automatically doing a lot of the segmentation for EyeWire and then taking that last bit that the neural networks couldn't do, and that's what was put into the EyeWire game. So Mohammed came back, and he actually, so I don't know why this is this part of it. So this is just to say, you might recognize this face in the room. So the way it was actually right at that time. That's why it's right here. So it was right at that time that Mohammed came back and he said, oh, I think I can solve this problem using convolutional neural networks. And then we don't need a whole other game to do it because there's sort of this ethical obligation. We don't want to waste human time if a machine can do it. So it was around that time that Leah, who knew about the EyesOnALZ project, mentioned it to Vani. And then Vani contacted us and said, yeah, I'll leave it there so you can take the picture. And then sort of the rest, Vani was very supportive and then kind of helped us get underway. So we could, and she fast-tracked us, which was great because we were really in a hurry to do this because we had a user community that we were building, and doing it the old-fashioned way was taking a long time. They were hungry for data, and this allowed us to develop and test these automated, methods. So then my other colleague, Yeva, I'm not going to try to say her last name. I've known her for 3 years, and I still can't say her last name. But she's done most of the software development and a lot of the data science work, including this machine learning stuff. And she came up with a model to automatically detect these sort of what we call bad vessel movies and clean out the data set using this. So this was another way that we use the compute resources on Azure, was to automatically detect these different varieties and also to classify and taxonomize and keep track of how many of these were occurring. Yeah, sometimes we're sort of whimsical, and so you've probably heard of Galaxy Zoo, this other citizen science project where you go classify galaxies. So this is not the Deep Sky survey. This is from our blood vessel data. But a lot of these things look like galaxies, so we did a galaxy classification of the blood vessels. In any case, so we've achieved 92% accuracy in cleaning up the data and removed about 20% of the movies. So that's speeding up what the humans can do by about 20%. And the 92% is good enough. We just need to validate that there's no selection bias in that 90%. So the final aspect is this classification task, which is what the stall catchers game does. And the basic idea here is, of course, they tried using machine learning first. And the machine learning algorithms could classify flowing versus stalled and get it right about 85% of the time. So, and they were using the best off-the-shelf computer vision algorithms at the time, and anytime something new would come out, they would try it. So the problem is this, that the value in the crowd is not that individual members of the crowd are better than the machine algorithms. It's just that they make different mistakes. We're all different, and there's diversity in our cognitive styles and approaches. So, when you have three, machine learning algorithms that are all the same algorithm, they're all going to make the same mistake. So it doesn't matter if you try to combine results from three different algorithms. On the other hand, you could have three humans, each of which is underperforming the machine learning algorithm, but in combination and in aggregate, you can have something that's very expert-like. I think one of the talks, since we were here, was about combining different machine algorithms, and that's an interesting approach as well to this kind of problem, and one that we're going to run a competition, and we'll see how much more we can do with machines. So the question for us was, how many humans do you need to combine to answer about a single vessel and have expert-like performance? We used some just very basic averaging methods at the beginning, and we had to hit these very high sensitivity and specificity numbers. So we realized that as we increased the number of annotations, it wasn't until we got to 20 annotations for an individual vessel that we had expert-like performance. That's a lot of human eyes on just one vessel, and it didn't feel very efficient. So we continued to refine our methods, and we think we're close to the theoretical limit, but we were able to, through and I won't go into the details of it, but to come up with a more dynamic method that involves some weighting and monitoring of individual performance to get it down to about 7 people per vessel. So ultimately, we were able to validate our approach, and so then they gave us real data to analyze, and then something happened. We gave them our results from the analysis, and then the lab said, we gave you a data set that hadn't been analyzed, but we actually kept part of it and analyzed it ourselves just to double check you. There's not really strong agreement between what you're giving us and what we came up with. So we sat down with them, and we realized that we actually had better agreement between our crowd and their individual experts, particularly when you looked at only the vessels where there was consensus between their experts and our crowd. And then in the remaining vessels where there was disagreement, we sort of talked about each one, and ultimately they agreed that that they had been wrong and that the crowd was right. So we felt sort of vindicated about that, and we like to brag about that. So now we're well underway. Like I said, we have these new data sets in the process. And we also realized that even though it takes humans using this approach to achieve the kind of accuracy that we need, that there might be some very easy blood vessels where a machine-based system could, with almost perfect accuracy, do the annotation. So then it was a question of, can we come up with a way for the machine to not only classify blood vessels as flowing or stalled, but also tell us how confident it is about its result and do that reliably. And so another way that we're sort of innovating in the machine learning space, and by we I mean Yeva, is to to build and test models like this on Azure. And so far, in our early efforts, we've been able to classify 5 or 10% of the vessels with perfect accuracy using a machine-based method. So that's, again, 5 or 10% fewer vessels that humans need to look at. So the overall impact of the work we've done with our initial Azure grant over a 6-month to a year period of time was to completely remove this other bottleneck of tracing the vasculature using automated systems. We've removed 20% of the movies which were bad, and we believe, we haven't put this into our pipeline yet, but it looks like we'll be able to at least reduce the human load by around 10% in terms of the vessels that need to be annotated. So half our work is in terms of engaging the community, and the other half is improving the efficiency of our platform. And the combination of those two things addresses our bottom line, which is analytic throughput. All we care about is getting to a treatment target faster, and so through our data science efforts, we focus on this analytic on the improving the efficiency of the platform. So So the work we want to do next is basically to improve the sensitivity and specificity of our auto tracing. So we're not auto tracing perfectly right now, which means that if we get an image stack that has 1,500 vessels, maybe we're only using 1,000 of those. If we can improve that, then we can squeeze more data, and then maybe the lab scientists don't have to collect as much imagery, so that can speed up the research further. As I mentioned before, we need to make sure that as we remove bad movies, that we're not, sometimes we have false positives in that, and that those false positives aren't pulling out more stalled vessels than flowing vessels, that there's not a selection bias there. And we really want to, as I mentioned, through sort of introducing more and different kinds of machine-based algorithms, possibly in combination, start to increase the proportion of classification that's being done by machines, so the humans really are doing less work and focusing on only the very most challenging problems. And we're always seeking to improve the efficiency of our wisdom of crowd methods. So even though we think we're near the theoretical limit, we think there's there's always possibly room for improvement there. And the other thing is that we've been approached by researchers in other disease research areas who realize that our platform could be applied to their data. There's a researcher at University of Pittsburgh who's got huge data sets of sickle cell anemia data. The difference there is that instead of looking for flowing or stalled blood vessels, they want people to pick out what are called tortuous vessels. So instead of being vessels that have a nice kind of flowing shape, they're sort of all twisted up. That's, I think, the hallmark of the sickle cell. I guess the last thing I'll say is that we've set our sights big. We do a lot of sort of community engagement events. Sometimes they're synchronized, what we call catchathons, where everyone plays stall catchers for the same exact 1 hour period of time all over the world. We've done 2 international catchathons, and it's been a great way to build our community and generate a lot of excitement around what we're doing. We're aiming high. We're going up a couple orders of magnitude here, but we have a lot of reasons to believe we can do this. We're aiming for April 13th of 2019. What we want to do is engage 100,000 participants all at the same time, all within the same 1 hour period, primarily through libraries and schools where we have some inroads. We're creating a meetup capability that'll bring people together in those venues for that time. We want to analyze an entire research data set that would normally take 6 months or a year and answer a single research question in that 1 hour. And we, fortunately, will have a lot of help in doing that. So that's it. Thank you.